And welcome back to a riveting lesson in calculus. Okay, today we're talking about Newton's law of heating and cooling. Newton's law of heating and cooling tells us that the temperature of a hot object will decrease at a rate proportional to the difference between its temperature and that of its surroundings. Similarly, a cold object will heat up at a rate proportional to the temperature difference between the object and its surroundings. So my question of the day today, if you put the cold water and the boiling water in the freezer at the same time, which one freezes first? The cold water will freeze first, but the boiling water will change temperature faster, and that is because the difference between the boiling water and the temperature of its environment is greater than the cold water and its temperature of its environment, okay? So the graph on the board I drew is actually upside down from this graph. So this one is something that's really hot, like an oven, and if you put something cold in the oven, what's that object immediately going to start doing? It's going to start heating up, right? Now, notice that the bigger the temperature difference, like the first moment that you put that cold object in the oven, it's going to change temperature faster, because there's a bigger difference. As it gets closer to the temperature of the oven or the surrounding environment, the rate of change is going to slow down, so you notice that this slope is less steep than this slope, okay? Now, can the object ever get hotter than than the oven that it's in? Technically, no. That oven is kind of like an asymptote, and your object, any object, it doesn't matter if it's in an oven, in a freezer, if it's just in the air, if it's submerged in water. My husband and I really like to use the sous vide to cook. You guys heard of the sous vide? The sous vide is amazing because it makes the temperature of the water one temperature, and then whatever you put in it, the meat or whatever, is going to come up to that temperature, but it will never pass that temperature. So you can cook a perfect rare steak at 140 degrees, or that's not rare, but and you can leave it in there for 3 hours and it will never get more cooked than that, because it can never get hotter than that, which is awesome. This is a technique that fancy restaurants use, so they can just pull it out and sear it, and then it's ready to go. No, I eat it medium. Yeah. So that would be the same thing if you're sticking something into the freezer. Pretend this is backward, but it would drop in temperature. But the closer it got to the temperature of its environment, it would slow down its rate of change. Okay, so let's write this. Let's highlight this. The rate of change of the temperature equals a constant, so some constant K, times the difference in the temperature of the object and that of the surrounding air or the surrounding medium. So it doesn't have to be air, it can be surrounded by water, whatever the surrounding medium is. This is the temperature this is the differential equation we use for Newton's law, okay? A couple things. We need to know what all these letters stand for. H is the object's temperature. H is the object's temperature. Why would we use the letter H for its temperature? Heat. It's heat, yes. How much heat does it have? So we're going to call capital H is the object's temperature. So whatever you're putting in the oven, whatever you're putting in the freezer. And this big T, capital T, is going to represent the temperature of the oven, the temperature of the air, the temperature of your freezer, whatever the surrounding medium is, okay? This is in degrees Celsius for this problem, but the unit can change, okay? All right, so we have a yam. A yam is put into an oven. It heats up, I guess it's Thanksgiving or something, heats up according to the differential equation, dH dt equals negative 0.027 times H minus 200. So for this example, T is in minutes. Usually you put something in the oven for minutes, right? 30 minutes, 45 minutes. Usually it's not hours unless you're cooking like a big turkey or something. All right, so here's your slope field. All right, let's talk about this. So down here, this is your time. Which letter do we use for time? Ooh. I don't know. Little t. Okay, so we got two t's at play here. Little t is the time. This is in minutes. And temperature, this is referring to the temperature of what? The yam, the temperature of your object, in this case the yam. What letter do we use for this axis? That's H. Big H is like the heat. How much heat does your object have? Okay. So this is in minutes. This for this problem, this is in degrees Celsius. All right. So there's your slope field. What is the temperature approaching? How do you know it's 200? Right here. So this number right here, that's the temperature of your environment. And what does on the graph, what does that look like? It's the asymptote. So up here, this is the oven. The horizontal asymptote is going to represent that temperature of the environment. In this case, the temperature of the oven, it says it's 200 degrees. So in the equation, that's the big T. Okay. Now this constant here just talks about the rate of change. That's your constant of proportionality there. Okay. So this is 200 degrees Celsius. B is the yam heating up faster in the 5-minute interval from 10 to 15 minutes or in the interval from 30 to 35 minutes.
10 to 15.
Explain.
Because you're getting closer to your
it has more heat to gain during that.
So when it's earlier,
the rate is.
let's mark this on here. Let's say that this is a span of 1 hour. So put your 60 here. Let's put 30 in the middle. This is 15. Let's call this 45. Okay, so from 10 to 15 is that piece.
Yeah.
And from 30 to 35 is that piece. So we're comparing that to that. And yes, right here it has so if you're looking at the graph, it does have a steeper slope. But if you're thinking about Newton's law, tell me again what you're saying. What did you say?
It has more heat to gain.
Right. So there's a bigger difference in the temperature, right? This is a bigger difference in the temperature from the environment than this one. So whichever one has a bigger difference from its environment is going to be changing temperature faster. So earlier equals bigger difference in temperature. And if there's a bigger difference in temperature, that means you have a greater rate of change. Greater rate of change. Cool. That's basically what Newton's saying. The bigger the temperature difference, the faster the temperature is going to change. The other thing he said is all objects just want to be the temperature of their environment. Right? If you take ice cream outside on a summer day, that ice cream wants to be the same temperature as it is outside, so it melts. If you stick something in the freezer, it wants to be the temperature of the freezer and it's going to freeze. So we all know that. All right, down here. Right here we have some graphs. These are basically just snapshots in time. So again, this is time and this is the temperature of the yam. But if you look, you see there's a little cursor here and it's showing you, where did it go? It's showing you where the yam is at different times. So this first one, it says that the time is 0. And right here, the temperature of the yam, that's your H, is 20. So basically, we stuck this yam in the oven and we just took different temperature readings. Okay? So at 0 minutes, H was 20. At 5 minutes, H was 42.7. At 10 minutes, the yam's temperature was 62.5917. Again, these are in degrees Celsius, right? At 15 minutes, 79. 30 minutes, 119. At 150 minutes, how much time is that? 150 minutes.
2.5 hours.
So 2.5 hours later, the yam's temperature is 196. What is the yam's temperature approaching?
200.
Yeah, that oven is 200. Will the yam ever get more than 200? Mathematically, no. In real life, possibly from the way ovens work. Do you guys know how ovens work? Ovens can either be on or off. And so if you set your oven at 375 to make cookies, what it does is it heats it up past 375, shuts it off, It cools down, it turns it back on, it heats it up, shuts it off, and so it just turns it on and shuts it off and tries to keep it at a stable temperature, but it's actually impossible for it to stay at a constant temperature. So it might waver a little bit if you didn't know that. What?
Then how do you just, I guess, never mind. I said, how do you know that?
Well, you can hear my oven clicks every time it turns on, and it clicks and it turns off, and clicks and it turns on. It turns on and off, yeah, because it's either on or it's off. It can't like actually turn it exactly to 375 degrees. It's just on or it's off. So, okay, let's look at these little snapshots and answer these questions. What was the yam's initial temperature?
20 degrees Celsius.
Does that make sense?
Yes.
I know that we live in America and we use Fahrenheit here, but what is 20 degrees Celsius about in Fahrenheit?
It's about 60 something.
Yeah, in the 50s.
Do you remember the conversion rate?
It's like 27.
It's 9/5 times 20 plus 32. Okay.
I was just going to be wrong.
So why is the yam 68 degrees?
That's the common, like, room temperature.
That is, it's a kind of a cold room temperature, but that's about room temperature. Maybe you had the yam in the fridge and you took it out and you set it on the counter while you were getting everything ready. So it's about at room temperature when it goes in there, okay?
What's your house temperature?
It's just like 74.
Oh my god.
Wait,
I have a very large house and it costs a lot of money to air condition it, so like 74 is fine. That's fine. Yeah. Okay. How long will it take the yam to reach 120? So look at these times. Find the 120.
So, pretty much like it'll last.
That's right here, 119.9. That's 30 minutes. You could put a squiggle, about 30 minutes. All right, estimate how fast the temperature was changing 10 minutes after it was put into the oven. 10 minutes after it was put into the oven. We are going to estimate this rate of change two different ways. One, we're going to use a symmetric difference quotient. And the other one, we're going to use, well, do we have a formula for the rate of change of the temperature?
-0.027.
Okay, here's the equation they gave us. So, give me another color. So 200 is my big T, and the negative 0.027, that's the K. That's my constant. T is the temperature of the environment. H is the temperature of the yam. dH dt, what does that mean again? For this problem, what does it mean?
Change in heat. Or the rate of change of the heat. Is it rate of change of heat?
Of what? For this problem, for this example we're doing.
Of the yam.
It's how fast is the temperature of the yam changing in the 200 degree oven over time, right? Just
Okay.
want to be specific there. Okay. Now, what's the only variable in here? H, which means that the rate of change of the yam's temperature is only dependent upon what? Upon its temperature. It doesn't matter how long it's been in the oven. It's just what's its temperature, because its rate of change is directly proportional to its temperature, right? Okay, well, do we know the temperature at 10 minutes? What? How fast? Or how much? Okay, right here. At 10 minutes, the yam's temperature was 62.5917. So we're going to take that temperature, we're going to stick it in this equation. Go ahead and calculate what is dH dt when the temperature of the yam is 62.5917. Everybody grab your calculator and type this in. We're going to round to 4 decimal places. Oh no, that's okay. Smudged. So you're writing down your answer with 4 decimal places, and then you're also coming up with a unit. You need to be careful with your unit. We're looking for dH dt. This is a speed. This is a rate of change. What did y'all get?
3.71.
3.7100 is what I got. That's the best that we can do because we used all of those decimals. And what's the unit for this rate of change of temperature over time? Degrees Celsius per minute. Make sure that you put the C, because if you just put degrees per minute, degrees what? You got to be specific, okay? Okay, so after 10 minutes in the oven, the yam is changing about 3.7 degrees per minute. Now I want to calculate this another way, and that's what I underlined, the symmetric difference quotient. Let's start with the, people are like, what's a symmetric difference quotient? Okay, what's a quotient? Division, great. What's the difference? Subtraction. Okay, what does symmetric mean?
Equal.
Symmetrical. It's the same amount, it's like a reflection, it's the same amount on both sides. Okay, so think about what those words mean when you forget what's a symmetric difference quotient. It's a reflectional subtraction fraction.
Say that 5 times.
It's a symmetric. It's a reflectional subtraction fraction. Okay. It's your delta y over delta x. It's a change over a change. Now I want to, let's write that down. So d h dt is the same as delta h over delta t. In other words, now instead of taking one data point, which to find the derivative you only need 1 point, but to find the average rate of change you need 2 points, right? So this number that we found right here, let's write this down. This is the instantaneous rate of change, ROC, and I only needed one temperature to find the instantaneous rate of change because I used the derivative, and that's what calculus is good for. But if we didn't have that equation, if all we had were these temperatures and times, could you figure out how fast the temperature is changing at 10 minutes? Yes, let's pick 2 times where 10's in the middle. 5 and 15. So I know the temperature of the yam at 5 and 15 minutes. Are those symmetric to 10? Are they both the same amount of distance from 10? Yes. Is that the only option I have?
No.
Yes.
You can, well, probably.
Yes.
On those ones?
Yes.
0 and 30? No. That's 150. Okay, so we have no choice here. We got to use the 10 and the 15. So right here we're doing h of 10 minus h of 5 over 10 minus 5. If you want to do this on your notebook so you have more space, that's fine. So there you go. This is an average rate of change. Subtract the 2 temperatures from the, did I write 10? I meant
15.
to write 15. I'm sorry. Why did I have 10 on here? Oh, I did it over here. Whoops. Never mind. I'm going to write it over here. Okay. This is average rate of change. Delta H over delta T. So we're doing h of 15 minus h of 5 over 15 minus 5. Okay, so we're going to pull those snapshots here. H of 15 is 79.9442. H of 5, the temperature of the yam after 5 minutes was 42.7311. And then 15 minus 5 is the 10 minutes that passes between 5 and 15. So then what does that give you? 3 point, it should be close to this. 3.7, I got 7213.
Yeah.
And then this is also in degrees Celsius per minute. So look how close these two rates are. Here with the average rate of change, I use a symmetric difference quotient, again a subtraction fraction. That's your slope formula. I got 3.72. They're very close. This was the instantaneous rate of change using the derivative. And I also got 3.71. So they were very close to each other.
Where did the negative 42 come from?
That's the temperature of the yam at 5. So I did the 15 and the 5. I
No.
pulled, so if you're confused, I pulled these two temperatures and subtracted them here, and then these two times and subtracted them here.
Yeah, I just thought that was fraction, negative 42
Okay.
over 10. I was like, that's-
Over here I was getting ahead of myself. Does anybody have any questions about those two methods? What equation do I use to find the instantaneous rate of change?
The top
The
one.
1.1.
The differential equation, the derivative, right? And then to find the symmetric difference quotient, you're just doing slope. Okay.
Symmetrical subtraction.
I was getting ahead of myself. Estimate the rate of temperature change at 7.5 minutes. So that's what I was doing here. Sneak peek. Can I find the instantaneous rate of change at 7.5 minutes?
No.
Why do you say no, student?
Because there's no little t temperature for that time.
Yeah, because we don't know the temperature of the yam at 7.5 minutes, okay? So we can't use the instantaneous rate of change, but we can use... What two times would I use, though?
10 and 5.
10 and 5.
For 7.5... Oh, say that again? Can I use 0 and 15?
If you want to be lame, yeah.
No, but can I use it? Is it symmetric?
Yeah, but
Yes.
wouldn't it
Okay.
be different from 5 and 10?
Yeah, it would be different. Which one would be more accurate?
5 and 10.
Yeah, so you're going to pick the two that are closer to your midpoint. Use the 5 and the 10 because the 5 and the 10 would have a more accurate change than doing the 0 and the 15, right? Your slope would be more accurate. Okay, so go ahead and calculate that. You're pulling the temperature of the yam at 10 minutes and 5 minutes. Subtract those. Divide by the difference in time, 5 minutes. And then the answer is 3 point something.
Oops, I did that wrong.
Did you get this one?
3.9721.
9721, and my unit is degrees Celsius per minute.
Do we still just do 4 decimals if it's an exact number?
You need at least 4. If it stops, you can write all of them. If it doesn't stop, you need 4. At least 4. Okay. What are your questions about that? Is everybody okay with how I got that? I didn't write down the actual numbers, but I just did 62.5 minus this 42 divided by 10 minus 5. What's your name? Here it is. I can't say it out loud.
Student.
Student. Here you go, student. Have fun. Okay. Number D. Use Euler's method with an initial condition of h of 9 equals 59 and a step size of 0.2 to estimate h of 10. So we're going to need some paper for this one. Where's my paper? Party paper.
I mean, are your other classes really going to get this far?
That's why I'm recording this lesson. Okay, now if everybody's cool, we're not going to sit here and do Euler's method because we practiced that enough, okay? But let's just talk about it. So this is part D. If I were to use Euler's method with initial condition of h of 9 equals 59, first of all, what does that mean? H of 9 equals 59 for this problem.
9:59. The temperature of the yam at 9 seconds.
9 minutes.
Is
59.
okay, so this is saying I took the temperature of the yam after 9 minutes in this 200-degree oven, and it was 59 degrees, okay? It's saying use a step size of 0.2 to estimate what does h of 10 mean. Let's write this down. What does h of 10 mean? It means the temperature of the yam after 10 minutes in 200 degrees Celsius oven. You have to be able to explain what you're finding to me. You got to be able to explain it. Okay, so we won't do Euler's method, but how many times would I have to do this?
5.
5 times? Yeah, so between 9 and 10 is 1 unit. Divide that by a fifth. I would have to do Euler's method 5 times with a dt of 0.2. Here's my initial condition. H of 9 was 59. And H of 10, I'm just going to tell you, if you did Euler's method, you would get 62.766 degrees Celsius. What was the temperature of the yam at 10 minutes from these snapshots? 62.5917. Oh, look how close there. So Euler's method would get us a really good approximation. That was the actual temperature that we pulled. Okay. All right. For part E, find H of t, the particular solution to the given differential equation with the initial condition H of 5 equals 42. So it's telling us the temperature of the yam after 5 minutes in the oven is 42 degrees Celsius. We're going to use that to find a particular solution to this. All right, so everybody write this down. We're going to solve that equation. Here we go, dH dt. You will have to do this on your test. dH dt equals negative 0.027 times H minus 200. We're also told that H of 5 equals 42. What am I solving for? Yeah, I want to solve this for H. Okay, so now what's the next step when we're solving a differential equation?
Make the variables on the same side.
Okay, separate our variables. So this is going to be dH over H minus 200 equals
negative 0.027
dt. Separate your variables. Oh, we're going to take the integral of both sides. Did that come out of me?
Yeah.
Michelle B. Nelson. Just call me Cardi B. Nelson. No, please don't. Please don't.
You just said your full name.
They call me Spicy Mommy Hot Tamale. No, they don't. They do not call me that. All right.
You should leave that in the YouTube video.
It's in here, guys. It is in here. Take the antiderivative of dH over H minus 200. That is a natural log. This one? T plus C. Little t. Make sure your little t and your big t's look different.
For sure.
Alright, got to get rid of the log. We're going to exponentiate both sides. Cancel. H minus 200 equals E to the negative 0.027t plus, that's a C1.
Could we skip to where we just say C2?
Yeah, you can. Negative 0.027t times e to the C1. We know that this guy is our C2. So if you would like to skip that, you can just say H minus 200 equals C2e to the negative 0.027t. So my simplified, can somebody let that student in? My simplified equation for h of little t would be C2 e to the negative 0.027t plus 200. Questions about that? I'm going to cover this up. Whoa, what does this look like?
Oh my goodness, C2 to the EKT.
C e to the kt.
Same thing.
Wait a second. We knew that was k.
We missed this general one.
That's the general solution. Oh, look, this is k. But look, there's this extra thing on the end. What's that? That's big T. That's the temperature of the environment.
Yeah,
So,
I'll do it
in
next
fact, the heat equation for Euler, we can just use H equals C e to the kt plus you add the temperature of the environment. So the formula for Newton's method is the same as our population change, but we also have to tack on the temperature of the environment. So you do not have to solve this on the test. If you memorize this equation, all you need is what's my K and what's my T. That's it. If you can tell that from this equation, then you can just skip straight to here and plug in your K. Right, here's my K, here was my T in the differential equation. Yay! Okay, but now I need to find the particular solution. You can just write C. Yeah, we need to figure out what the C is, but what's the only way we can find C? Oh, we need an initial condition. We need a point. There you go. Your point is 542. Go ahead and plug 5 in for the little t. Plug the 42 in for H, and now we're solving for C. This was my general solution. So you will have to do that on the test. You will have to plug in a point and find the C, but they already tell you the K and the big T in the differential equation. Okay, so 42 equals C. E to the negative 0.027, my time is 5 minutes. This is a plus a big 200. I'm going to start by subtracting 200 from both sides. And that gives me negative 158. Up here I'm going to multiply negative 0.027 times 5. That gives me negative 0.135. Then I divide both sides by e to the negative 0.135. E to the negative 0.135. Cancel. Alright, so C sub 2 equals negative 158. E to the... If I bring this up, now it's to the positive 0.135. So I divided, it was still negative, but if I bring this up, now it's e to the positive 135. So take that, plug that back into here. So here's my heat equation for the temperature of the yam. It's going to be negative 158 e to the 0.135. So that's going in here for C2 times e to the negative 0.027 t, and then plus a big 200 over here. What else can I do to simplify that?
Just add to it.
Combine your e's together by adding those exponents, and my final answer, my particular solution, PS, would be negative 158 e to the negative 0.027 t plus 0.135, and then plus a big 200. Woo! Yeah.
We did.
The last thing that I want you to do...
You just had that.
It's gonna happen either way.
It's okay. It's okay. Alright.
Can't take this.
We know what the temperature of the yam is at 10 minutes from this, 62.591. You didn't do it, but I did Euler's method. And I got an approximate value of 62.766. But now that we have a particular solution, now you can use this to calculate. Part F says find the temperature of the yam after 10 minutes using your particular solution. So we're using our particular solution to calculate h of 10. What am I plugging the 10 in for?
Little t.
The little t. Little t times 10 plus 0.135 plus a big 200. Be careful when you type that in. Let's round your answer to 4 decimal places, please. My answer starts with a 6, as do all of these answers. 60 something.
Oh, why don't I...
Try again. Be careful how you type it in. Should be 60 something. Oh, I'm sorry. Where did my negative go? It's a negative.
So what?
Sorry, I had it here and I had it here. I just forgot to put it there and there. Also, if you type it in and you get like a negative temperature, is it possible for the yam to have a negative temperature?
No. No.
After being in the oven any amount of time? No, that's freezing cold. That's colder than your freezer, a negative temperature. In fact, if you tell me that the yam is a negative temperature, I'm going to write brr on your test because there's no way that your yam can be a negative temperature. Like, no, you did something wrong. Go back and check your signs. Check your numbers. It will not be a negative temperature. I got 61.9529 and the unit is
Something wrong.
degrees Celsius. Degrees Celsius. Okay, on Monday we will do some problems using Newton's law, but your homework is due on the population questions. That's page 18, everything but 11. And really, number 8 we already did in class, so we're not going to grade that one. It's just 9, 10, 12, 13, 14, and 15. Oh, you know what? We didn't talk about half-life, did we? Let me pause this video here.
Halfway.
Hold on.